Okay, this was the second problem that had to do with equivalence classes, which also caused a lot of difficulty. So let's go ahead and try to solve this problem. So let A be this set of letters, 1, 2, 3, 4, 5, 6, 7 letters, and W is 3 words, 1, 2, 3. So I'm defining a relation on A. So W is only used to define the relation. We're not going to have elements of W in our equivalence classes. Two letters in A are related if they're both in the same number of words in W. Now here are two examples. T is related to O because T is in 2 of the words in W. T is in 2 and T is in 3, but it's not in 1. And similarly, O is in 2 words of W. O is in 1 and 2, but not in 3. As another example, P and Q are both in 0 words in W. So first question was draw a digraph that represents the relation twiddle on the set A. So it's quite clear that the membership in equivalence class depends on how many words the letter is in. So let me just list these letters: N, O, P, Q, R, S, T. And here I'm going to list the number of words that each letter is in. Okay, now N is in how many words? 1, 2, 3. It's in 1. So it's in 1, but not in 2 and in 3. 0, we know O is in 2. P is in 0. Q is in 0. R is in 1. S is not in any of them. And T is in 2 of them. All right. So from this we can tell which ones are equivalent. We already know that R and T are equivalent. So we'll do R and T like that. So we can draw a two-way arrow like that. Now, one thing that everybody missed, or almost everybody, is that R is also equivalent to R. So we can draw that arrow, and we can draw that arrow as well. Right. Now sorry, why did I say R? It should be O and T. So scratch that and go back. Okay. So O and T are in 2 letters. Are in 2 words. So O and T have these arrows and also go to themselves. Now, are there any others that are equivalent? Well, P, Q, and S are all equivalent to each other. So I could do that like this. P, Q, S, and they're all equivalent. So I have a double arrow here, double arrow here, a double arrow here, and I also have the loops that indicate that they're related to themselves. Okay, that's called a complete graph, but everything there is related to itself. Okay, so that takes care of PQR, PQS. Okay, then we have R and N. So we have N and R. These are also related to each other. So we've got a two-way arrow there, and we have a complete graph here. So that shows all the relations. Every relation is expressed in this way. Now, to express as a list of a subset of A cross A, that's a little bit long, but we can still do it. We just need to list the pairs associated with each one of these arrows. So for instance, here I have OO, and I have OT, and I have TO, and I have TT, and that's from the first graph there. Then from this graph, I'm going to get, similarly, NN, NR, RN, and RR. And then from this graph, I'm going to get QQ, QP, PQ, PP, and I'll have PS and SP, and I'll have SS, whoops, and then I'll have SQ, and then I'll have QS, and I think that's everything. To make sure you have everything, you can count the arrows: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12, 13, 14, 15, 16, 17. 17 arrows, so that's complete. Now, as far as the partition goes, you can see the partition up here. You can see that O and T are equivalent, that's one class, and R are equivalent, and PQS are equivalent. So the partition is the three sets OT, NR, and PQS. Okay, so that's the partition. Okay.